Okay, let's dive in. There's this massive shift happening, or potentially happening, in generative AI computing.
Yeah, definitely.
So today's deep dive is really for you if you're watching the field and thinking, wow, the energy costs are just ballooning. Yeah. We're looking at something pretty different.
A completely new architecture.
Exactly. A specialized computer architecture designed from the ground up for efficiency. We're talking about thermodynamic sampling units.
And the context here is, well, it's critical. The AI boom we're in, it's incredibly power hungry.
We're not just talking small numbers here, are we?
No, not at all. It's on a globally significant scale. Some sources are projecting that by 2030, just the large US AI data centers could be pulling something like 10% of all energy produced in the US.
10%? That's huge.
It's astronomical. And the cost, well, the cost for that kind of build-out rivals the entire Apollo program adjusted for inflation. It just doesn't seem sustainable with current hardware.
Okay, so that really sets the stage for this new tech, Thermodynamic Sampling Units, TSUs. And they run something called Denoising Thermodynamic Models, DTMs.
That's the core idea, yes.
And the mission, really, is to break away from this GPU dominance, right? And potentially offer this massive efficiency gain. What was the number? 10,000x?
It's a headline number, yeah. Up to 10,000 times more efficient than current top-tier accelerators for certain tasks.
It sounds almost too good to be true.
Well, it sounds like sci-fi, but the claim really stems from tackling a fundamental mismatch we've had in computing for a while now.
Ah, right. You're talking about the hardware lottery. Can you unpack that for us? Because it sounds like it's the whole reason TSUs even exist.
Yeah, absolutely. So generative AI, what is it? Fundamentally, it's about probability. It's generating stuff by sampling from these really complex probability distributions.
Okay.
But we run these things on GPUs. And the hardware lottery idea is basically that GPUs were initially designed for graphics, pushing pixels, lots of matrix math.
Right, for video games and rendering.
Exactly. And then it was kind of accidentally discovered that, hey, this architecture is also really good for deep learning training because that also involves a ton of matrix multiplication.
So we sort of lucked into a tool that worked, but wasn't necessarily the right tool for the job, especially the sampling part.
Precisely. It's like finding out your minivan is surprisingly fast on a racetrack, so now every race team has to use a minivan, even though a purpose-built race car would be way better.
Okay, I get that analogy.
And this historical accident, this lottery win, it sort of locked us into algorithms, think LLMs, standard diffusion models, that are specifically designed to minimize the actual sampling step.
Because GPUs are bad at it.
They're not designed for it. They're fantastic matrix multipliers, but they're sequential, energy-hungry samplers. It's just not what they're optimized for.
So the TSU flips that. It's built to be probabilistic from the start. But let's push back on that 10,000x number for a second. That sounds like, a best-case scenario on a toy problem.
That's a fair question. And yeah, the benchmark cited is often fashionamnist, which is relatively simple compared to, say, generating high-res images.
Right.
But the reason the potential gain is so large, even on that benchmark, is because the TSU isn't trying to be a general-purpose accelerator like a GPU. It's a thermodynamic sampling unit. Its one job is to take parameters defining a distribution and output samples from it.
So it's specialized hardware for the core generative task.
Exactly. And it implements the required physics, the Denoising Thermodynamic Model, directly in the silicon. That's where the efficiency comes from, doing the right job with the right tool.
And critically, the sources say this isn't based on some, exotic futuristic physics. It's buildable now.
That's a key point. No magnetic tunnel junctions, no qubits needing cryocooling. Extropic is developing an all-transistor probabilistic computer.
All-transistor, so standard manufacturing.
Standard CMOS processes, the same kind of tech that's in your phone or laptop. That makes it potentially scalable and, commercially viable. The breakthrough is figuring out how to implement these denoising models efficiently with transistors.
Okay, let's get into the nitty-gritty then. The physics, the actual circuit. The foundation is something called a pbit.
Right, the probabilistic bit, or pbit. That's the fundamental building block.
And what is it exactly?
It's essentially a small, programmable analog circuit. Its job is to implement a Bernoulli distribution, basically, to output a 1 or a 0 with a specific probability P.
And how do you program that probability?
You apply a control voltage. That voltage determines the probability P, and crucially, it's analog.
Why is analog important here? Aren't digital circuits usually seen as more reliable?
Usually, yes. But here, the analog nature is actually the source of the randomness. They leverage the inherent physical noise, like shot noise, that exists in transistor networks, especially when operating near the subthreshold region.
Wait, they're using the noise that engineers usually try desperately to eliminate?
Exactly. They're turning a bug into a feature. They're harnessing those natural stochastic fluctuations in the physics to generate the random samples efficiently. You set the probability with the voltage, and the circuit's noisy behavior naturally produces samples according to that probability over time.
Okay, that's pretty neat. But 1p-bit is simple. How do you connect these up to represent the complex distributions needed for AI? This sounds like it runs straight into the big problem with energy-based models, or EBMs, that normalizing constant Z.
You nailed it. That's the computational wall. So EBMs define the probability of a state, let's call it X, based on its energy, EX. Usually it's something like PX is proportional to E to the minus EX. Low energy, high probability, like a ball rolling downhill.
Makes sense.
But to make those probabilities sum to 1, which they have to do, you need to divide by this normalization constant, Z. And Z is the sum of E to the minus EX over all possible states X.
All possible states. If you have n binary variables, like np-bits, that's 2 to the power of n states, right?
Exactly. Exponential complexity. Calculating Z directly is computationally intractable for anything but the smallest systems. It's like trying to, I don't know, count every possible arrangement of atoms in this room just to figure out the temperature in one spot. It's impossible.
Okay, so Z is the villain here. How does the TSU hardware get around this fundamental problem? It can't be calculating Z.
It doesn't need to. It uses a technique called Gibbs sampling. It's actually been around for decades, used a lot in statistical physics.
Gibbs sampling, how does that work?
Instead of trying to compute the whole probability distribution at once, Gibbs sampling is iterative and local. You pick a node, a pi bit in this case, and you update its state, or 1, based only on the current state of its immediate neighbors in the network.
Just the neighbors.
Just the neighbors. The probability of flipping the bit depends only on the local interactions. By doing this iteratively across the network, the whole system eventually settles into configurations that are samples from the desired distribution without ever needing to compute Z. It cleverly sidesteps the global normalization problem.
Okay, so local updates bypass the global calculation. Let's connect that back to the hardware. You mentioned an EBM, maybe the Boltzmann machine example.
Yeah.
How does the physical circuit implement that local update?
Right. So imagine your probabilistic graphical model, your PGM.
Yeah.
Each node in that model maps directly onto a physical puck-bit circuit on the chip. The connections between nodes, the weights are implemented, often using resistors.
Okay.
Now, for a given puppet eye, the Gibbs sampling rule requires knowing the influence of its neighbors. This influence is basically a weighted sum mathematically. It's the bias term, gamma, which is like a local energy field, determined by the neighbor's states, xj, and the connection weights.
So the sum of weights times neighbor states.
Pretty much.
Yeah.
And the hardware does this calculation naturally. A linear resistor network connected to the puppet can actually compute this combined bias, gamma, as an analog voltage.
So the neighbor states and connection strengths directly create the input voltage for the target puppet.
Exactly. That calculated bias voltage, gamma, is fed directly into the control input of the Fubit circuit we talked about earlier.
And the Fubit's natural response.
The Fubit circuit inherently has this sort of sigmoid-like response function. The probability of it outputting a 1 depends on that input control voltage in a way that matches the conditional probability needed for Gibbs sampling. Pi equals +1 neighbors is basically sigma gamma.
So the physics of the transistor circuit is the math needed for the sampling update.
You got it. They're getting the correct update rule almost for free because of how the analog circuit behaves. It's a really elegant mapping of the algorithm onto the physics.
There's another trick to speed things up. Something about the graph structure.
Bipartite?
Yes, block Gibbs sampling. If you structure the connections in your PGM, the graph, so that it's bipartite, meaning you can color all the nodes with just 2 colors, such that no 2 nodes of the same color are directly connected.
Like a checkerboard pattern. Exactly like a checkerboard. Then you can update all the nodes of one color simultaneously in a single step, because none of them depend directly on each other within that step. Then you update all the nodes of the other color.
So you're parallelizing the updates within a block.
Precisely. It drastically speeds up each iteration of the Gibbs sampling process, the mixing, without making any individual update take longer. It's another hardware-level optimization that boosts efficiency.
Okay, so we have efficient updates using noise, Gibbs sampling to avoid Z, and block Gibbs to speed it up. That sounds all good. But the sources mention another big challenge. fitting these models directly to complex real-world data, the mixing-expressivity tradeoff, MIT.
Ah, yes, the MIT. This is a really important point, and it's kind of the reason simple EBMs or monolithic EBMs, MEBMs, haven't really dominated generative AI despite the elegance.
What's the trade-off?
Real-world data is messy and multimodal. Think about a data set with pictures of dogs and airplanes. In the energy landscape defined by an EBM trying to model this data, the dog pictures would be in low-energy valleys, and the airplane pictures would be in other separate low-energy valleys.
Okay, different modes.
Right. But to get from the dog valley to the airplane valley, the model has to go over a high-energy mountain pass, a huge energy barrier, delta E.
And the Gibbs sampler has trouble with that.
Big trouble. The Gibbs sampler explores the landscape locally. When it falls into one valley, say, generating dogs, it gets trapped there. It takes an incredibly long time, the mixing time, or K-mix, for the random updates to accumulate enough energy to jump over that barrier and find the other modes, the airplanes.
So the more complex and multimodal the data, high expressivity, the rougher the energy landscape, and the longer the mixing time needed to explore it.
Exactly. You get stuck. Training becomes unstable, sampling takes forever, and you burn a ton of energy just waiting for the sampler to mix. That's the MET.
Okay, so that sounds like a potential deal breaker for complex tasks. How does the Denoising Thermodynamic Model, the DTM, solve this MT problem?
This is where the DTM architecture gets really clever. It basically merges the ideas of EBMs with diffusion models, which have become super popular recently.
Diffusion models,
Yeah.
the ones that add noise and then learn to remove it.
That's the core concept. Instead of trying to learn one single, incredibly complex monolithic EBM, MEBM, that has all those sharp valleys and high mountains, the DTM uses a sequence of many simpler EBMs.
Chaining them together.
Yeah. It models a process that starts with pure noise and gradually denoises it over many steps, say T steps, to produce a sample. It's like reversing a Markov chain where noise was added incrementally.
And how does chaining simple EBMs avoid the MET problem?
The key is in how each step is modeled. The probability of going from a state at time t to the previous state at time t1 looks like this conditional probability, pxt1xt. The DTM models this using an energy function that has two parts. One part is the learned EBM for that step, a theta. But crucially, there's another part, a forward energy term, EF, that essentially links xt1 to x. It acts like a simple connection or coupling between the states at consecutive time steps.
What does that coupling term do?
It acts like a guide or a prior. It basically puts an energy penalty on states xt1 that are too far from the current state. This has the effect of making the conditional distribution pxt1xt at each step much simpler and smoother. It prevents it from becoming strongly multimodal.
Ah, so each individual step is easy for the Gibbs sampler. No huge mountains to climb within one step.
Exactly. You're breaking down the incredibly complex overall distribution into a sequence of much simpler conditional distributions. Each step only requires a short mixing time, a small K-mix, for the Gibbs sampler to work effectively.
So you get the high expressivity of the overall T-step process, but the efficient sampling of simple models at each step.
That's the core insight. You circumvent the MT.
And this sequence of EBMs is what the Denoising Thermodynamic Computer Architecture, the DTCA, implements in hardware.
Right. You can imagine chaining these hardware EBM blocks together on the chip, possibly even using distinct circuits for different steps if needed.
The diagrams also show these latent variables. Z, what's their role?
Ah, the latent variables. They're really important for scaling complexity. They are extra variables, kind of like hidden nodes, that are part of the probabilistic model at each step, but aren't directly tied to the data dimensions, like image pixels.
So they add modeling power.
Yes, they give the model more capacity, more expressive power, without necessarily making the energy landscape rougher in the data space. It allows the model to learn more complex features and correlations without dramatically increasing the mixing time K-mix. It's a way to decouple model size from data dimensionality to some extent.
Okay, that makes sense. Let's talk practicality again. For any of this to work reliably, you need that source of randomness, the noise generator and the probit, to be good, fast, efficient, small.
Absolutely crucial. And the sources indicate they have a solid solution here. The random number generator, RNG, they're using is also an all-transistor design.
Leveraging the same noisy physics.
Yes, those stochastic dynamics in the subthreshold transistor networks. It's apparently fast. The randomness has an autocorrelation time around 100 nanoseconds, which is quick enough for practical clock speeds. It's energy efficient, and importantly, it's small, so you can pack many p-bits onto a chip. This RNG seems viable for CMOS manufacturing.
And that feeds back into the energy savings. You mentioned the formula earlier, E equals TK mix L2 E cell. Can you break that down again in light of the DTM?
Sure, E is the total energy, T is the number of denoising steps in the DTM. L2 is roughly the number of variables or p-bits, like pixels in an L/L image. E cell is the energy cost per update of a single p-bit cell, which is tiny, estimated around 2 femtojoules.
So T, L squared, and E cell are somewhat fixed by the problem in the hardware.
Right. The game changer is K-mix, the mixing time per step. For a traditional MBM trying to model complex data, K-mix could be huge, maybe millions of Gibbs steps to ensure you explore all the modes.
Because it gets stuck in those valleys.
Exactly. But for the DTM, because each conditional step, PXT1, is designed to be much simpler, the required K-mix is dramatically smaller. The source material mentioned numbers like K-mix around 250 iterations.
Okay, 250 versus potentially millions. That's a massive difference.
That's the core of the 10,000x claim. It comes primarily from that massive reduction in K-mix enabled by the DTM architecture, combined with the inherently low energy per operation E-cell of the Fabit hardware.
Right. This all sounds incredibly promising on the hardware and physics side.
Yeah.
But if this is going to be useful, people need to be able to actually develop algorithms for it, simulate it, test ideas. That sounds like a software challenge.
A huge software challenge, and that's exactly where THRML comes in.
THRML, the Thermodynamic Hypergraphical Model Library.
That's the one. It's the essential software bridge. Think about it. Trying to simulate these large, potentially sparse hardware EBMs on a regular GPU today is, well, it's really painful for researchers.
Why is it painful? GPUs are powerful.
They are, but for the wrong kind of computation. GPUs excel at dense matrix operations on regular grid-like data structures tensors. Probabilistic graphical models, PGMs, which describe these EBMs, are often sparse and have irregular connections. Representing and sampling these efficiently on a GPU is awkward.
The data structures don't map well?
Not naturally. You end up with lots of indirect memory access, difficulty parallelizing the sparse updates, and often rely on slow, high-level Python loops to manage the graph structure and the sampling process, which kills performance.
Okay, so THRML is designed to fix that.
Yes, it's an open-source library built on JAX. JX is a popular Python library for high-performance numerical computing, particularly strong in automatic differentiation and accelerating code on GPUs and TPUs via XLA compilation.
So THRML uses JXXLA to speed up these PGM simulations. How?
It provides tools specifically designed for PGMs and EBMs. Key features include really efficient implementations of block Gibbs sampling, which we discussed. It supports graphs with different types of nodes, heterogeneous graphs, and lets node states be complex Python objects, binaries.
But how does it beat the slowness of simulating sparse sampling on a GPU? You mentioned Python loops being a killer.
This is where the internal engineering of THRML seems clever. Instead of directly representing the sparse graph in a way that forces lots of slow Python-level iteration for neighbor lookups during sampling, it compiles the structure of the graph, the factor interactions, down into a more compact global state representation. This allows the core sampling logic, especially the block Gibbs updates, to be expressed using JAX's array-level operations.
So it pushes the computation down into the fast-compiled JXXLA backend.
Exactly. It minimizes the Python overhead and maximizes the parallelism that the accelerator GPU-TPU can actually exploit. It makes simulating these otherwise tricky, sparse sampling models much more practical and faster than you could typically manage with standard libraries.
So researchers can use THRML today on GPUs to experiment with algorithms that will eventually run on TSU hardware.
That's the goal. It provides the necessary simulation environment and tools to explore DTMs and other PGM-based models, allowing the community to develop the software and algorithms in parallel with the hardware development. It bridges the gap.
Looking even further ahead, the sources mention hybrid systems, HTDML.
Right, hybrid thermodynamic deterministic machine learning. This seems like a very pragmatic direction. It acknowledges that TSUs are specialized, they are brilliant samplers.
But maybe not the best at everything.
Probably not. Tasks like, say, initial data preprocessing or learning complex embeddings to feed into the probabilistic model, those might still be better suited to traditional deterministic accelerators like GPUs or TPUs, which are highly optimized for that kind of dense computation.
So combine the strengths.
Exactly. Use a deterministic neural network running on a GPU TPU to do the heavy lifting of feature extraction or embedding, and then feed those results into a TSU running a DTM for the core probabilistic generation or inference task.
Is there any proof this works?
There was an early example mentioned using a small neural network to embed CIFAR-10 image data into a binary format, which was then processed by a DTM simulated using THRML. Apparently, this hybrid system achieves similar performance to a standard generative adversarial network, GA, but the neural network part was about 10 times smaller.
Interesting. So the probabilistic hardware handles the core generative load, allowing the deterministic part to be simpler.
That's the idea. It suggests a path towards systems that leverage the massive efficiency of TSUs for the sampling-heavy parts, while still using conventional hardware where it makes sense. And the scale is planned to be significant. The Z1 TSU chip is aiming for hundreds of thousands of these IBIT sampling cells.
You know, what really strikes me here is how this whole approach flips the usual optimization problem on its head.
How do you mean?
Well, for decades, we've been trying to make inherently probabilistic algorithms, like sampling, run efficiently on deterministic hardware GPUs, TPUs which aren't naturally suited for it.
Right, adapting the algorithm to the hardware.
Yeah. But this is the reverse. This is creating hardware that is natively probabilistic, perfectly suited for the core operation of generative AI, which is sampling.
It's designing the hardware for the algorithm, specifically for the physics of sampling.
And that claimed 10,000x efficiency gain, even if it's on simpler benchmarks initially, really underscores that. It makes the case for thermodynamic computing, for TSUs, as potentially a fundamentally new type of computational primitive.
I agree. It forces us to reconsider the bottlenecks. Maybe the limitation in generative AI hasn't just been the math or the algorithms, but the physical constraints imposed by trying to do sampling on matrix multiplication engines.
Because the hardware shaped the algorithms we thought were feasible.
Precisely. If you suddenly introduce hardware that makes efficient, fast sampling the easy part, the algorithms themselves will likely evolve. We might see models that rely much more heavily on sampling with short mixing times, simply because the hardware makes it cheap and fast. Just like algorithms shifted to maximize matrix math when GPUs took off.
It really changes the design landscape for AI researchers, doesn't it?
Completely.
So, thinking about the takeaway for someone listening, what does this all mean for you? If TSUs and DTMs gain traction, if they become a new standard alongside GPUs, well, the whole game changes.
Yeah, the fundamental constraint shifts. Energy efficiency becomes a primary driver, potentially enabling models or applications that are just too costly today.
It really poses the question, could we see a future where certain workloads, especially those heavy on generation or probabilistic inference, shift away from purely deterministic approaches towards these thermodynamic, probabilistic ones, just because the hardware makes it vastly more efficient?
It's definitely possible. Just as vectorized code largely replaced scalar code for performance on CPUs and GPUs, maybe we'll see probabilistic algorithms become the preferred tool for certain tasks previously dominated by deterministic methods, all thanks to this hardware shift.
It's a genuine paradigm shift to keep an eye on, especially when you consider the potential cost savings, both financially and environmentally, if that efficiency promise holds up at scale. Really fascinating stuff.